Okay. See, last time when I showed how this example that illustrated, where after doing a widening chain, an ascending widening chain, after you get jump over the least fixed point when you do widening chain iteration instead of linear iteration. And after that, when you do descending iteration. So there was a kind of mistake. It's not exactly a mistake, but I think that, it's that maybe I went through too fast that no one pointed out. So I want to kind of re-explain that to make a point as to how, say, after doing widening chain iteration, you get to a -1 to infinity as the fixed point. You stabilize to that. Now, that is a post fixed point in the sense that it is not exactly a fixed point. It's not a fixed point, but it is an over approximation of fixed point. Through descending chain, I showed you how we could get it down to -1 to 1,000. And I think, and through by applying the post, the F operator on that. But there is a subtle point there that I missed. See, this algorithm, the work list algorithm that I've shown here, it was really, maybe the details, at least the version that is shown here, it's a way of implementing, doing cleaning iteration, okay, on an arbitrary CFG, okay, given a set of fixed point equations for each location in the CFG. So it is meant to work, for that version. This works for ascending a chain starting from. That's why you initialize the value at every location to bottom, and then you apply you propagate the values at every location by applying the fixed point equation. Now, the same algorithm, a similar algorithm can be used for doing to work on descending chain as well. Okay, and for descending, implementing descending chain iteration. So there are two important changes that, so when you do descending chain iteration from top, you will the same thing will produce the greatest fixed point for each of the locations. Two significant changes there are that you will have to start this algorithm, the initial value at each location to be top, okay? Because that's what this is. And the other thing is that for all the equations here, in the fixed point equation, which involve, fixed point equation corresponding to locations which involve a join operation. So that is locations which have one or more than one incoming arrows. You used to use a join when you do ascending chain. Instead, you'll have to use a meet, okay, because you're descending down the chain. So that is the two important points that I forgot to mention. Okay. Now, after that, when you do this with those two changes, then you will converge into a greatest fixed point. Of course, you could do this linear iteration, this algorithm to perform linear iteration from instead of top. You could start from any post fixed point, okay, which is which is a reductive element, and therefore even for post fixed points, if you apply that instead of top, you will initialize at the post fixed point, and you will end up getting to a fixed point there. Now that's what I'm doing here. So what I missed showing you, everything was correct here. Okay, so after you get this post fixed point -1 to infinity, you have to apply the F corresponding to the while loop here, which I've shown here on the left side, to using the descending linear iterations. When you do that, so what happens? You'll have to propagate -1 to infinity through the loop, and that's what will get you -1 and 1000. Okay. After that, what you'll have to do is do a meet, not the join. Okay. Maybe last time I didn't. I glossed over that fact. It's only when you do the meet, then you end up reducing that -1 to infinity to -1 to 1000. After which, then you will exit. Okay, you will take the exit R, and you will then improve 1000 to infinity. This one, which was there earlier, to 1000. The interval 1000, 1000, and then that way you get the more precise invariant there, which avoids the spurious. Okay, that's what I wanted to point out. Okay, any questions you have? Okay, I hope you understood the point that I had missed last time. Okay. Yeah, doing clean iteration, you use this algorithm. But
does it mean that you have 2 iterations to do
that? I have to do 2 iterations. Why do you say that? Okay, so after one iteration, you get -1 to -1 to 1000. Why? Why do you say that?
On the left-hand side, you found out -1 to 1000.
This was wrong. Okay. No. Yeah. Oh, there's another mistake. Actually, this should be 999. Okay, because x is less than 1000. So you will get, so this will be 999 and this will be 1000. Correct? Because x is less than 1000, and therefore, when you pass -1 infinity here, you will then get to -1 to something less than the upper bound should be 999. That's a mistake. Okay, so in this one should be 1000. Okay, yeah, and yeah, I guess what you're saying is correct. So that will give it to, even with that, you will have, no, with that, what happens is you can't even, there's, after that one iteration, you don't need to iterate any further, because you can't even iterate, because this guard of the loop entry condition will get violated now. Okay, because you are from 0 to 1000 here. Okay, and that's what you will take it back, and you got yeah, it's actually, this should be 0 to 1000. So 0 to 1000. Yeah, it will be 0 to 1000. So several mistakes here. Okay, so this is not -1 to 1000. It should be 0 to 1000, because that's what you're getting here. And then after that, you won't even enter the loop. Okay, so you will exit, because this guard condition will get violated, and you will exit. Okay, yeah, in that sense, it is not 2 iteration of the Kleene loop around the while. It's just one, and you will exit the loop, because you won't get out. Yeah. Okay, so now let me get back to, so let's see if there are more people. Okay, so I will finish up the lecture. Hopefully they will. Yeah, this is not what I want. I'll have to get back to this. Okay. Make this slightly bigger. Hope this is good enough. Okay, so last time we were looking at predicate abstraction, another way of abstracting, potentially large or even potentially infinite state systems into finite state models, which by using a set of predicates that you wish to track. Okay, and we define how to abstract. There where the elements of your abstract systems are the possible valuations, different possible valuations for those predicates that the predicates evaluate to on these concrete states. And we were discussing this example, this transition system, a concrete transition system, and so this is the blues show the different possible abstract states, which are the different possible values that these predicates can take. And what is shown inside each of these boxes are the states that get mapped to that particular abstract state, because these two states actually satisfy this P1 and P2 condition. Okay, yeah. So this can, if you assume these are the only values over which, then this is a finite state to finite state abstraction. But if you assume that, okay, there are you're starting with a concrete system with infinite states where x and y range over natural numbers, then of course you have a lot more states in each of these blue boxes. Okay, so and this is that's how the abstract states are defined. Now, then, in order to make it into an abstract transition system, you will have to define what your initial state is and your abstract initial state for the abstract model is, and the transition relation for the abstract model. And that we saw, we defined it using existential abstraction. Okay, where was it defined before? I'm sorry. Yes. Okay, so whenever there is, if there is a yes, so every abstract state is included in the initial. It becomes an initial state if the concrete state, even if one of the concrete states that get mapped to that abstract state is hat, there even exists one which satisfies the initial condition of the concrete state. And that's why this is called existential abstraction. Even if one is there, this, that entire, all the states that get mapped to that particular abstract state will have to be included in the initial state. Okay? That is the constraint. Similarly, the transition relation is also defined as an existential constraint. Okay? That if there are two states, there will be a transition between two abstract states, S cap and S cap prime. If there must be a transition if there exists at least one state that get in the pre-image, that get mapped to S hat. There is that has a successor in the concrete set, successor inside the state to which S hat prime gets mapped, and that's how this existential abstraction. And now this is just the minimum. This is the constraint that it imposes. Of course, since it says that if there is such conditions, then there must be a transition. Of course, you can add more transitions, and so there are several different variations that are possible based on this existential abstraction constraint. But the one which adds the minimal number of states into the initial state on the abstract model, and the one that adds the minimal number of transitions as required by this constraint that is considered as the minimal existential abstraction. And that's what I was illustrating. With these things, with these two conditions, if an existential abstraction, then it satisfies. It ensures that it is a conservative abstraction, that in the sense, conservative in the sense it's an over approximation, that every path in the original thing is simulated in the abstract system as well. Of course, the abstract system can have more paths, since there are potentially more transitions and more states in the that become initial states in the abstract thing. But similarly, the reachable states, the set of all reachable states are also an over approximation. The set of all reachable states of the concrete model is guaranteed to be included in the abstraction of states. And therefore, this condition is always, when it is such an over approximation, then when you do check properties, safety properties on such an abstract model, which is based on an existential abstraction, the safety properties are guaranteed to be preserved. And that's why if you prove something on the abstract model, it will also be true for the concrete model. And that is the idea here. So for this one, we saw that the abstract transition, both these states, this P1, P2 will be an initial state here. And that's the only initial state because it's pre-image. It's concretized set of states. Okay, because there is one state, okay, which gets mapped to P1, P2. And you will see that there is also another state which is not an initial state, but that is also effectively satisfies P1 and P2. So in some sense, it is also gets included in that abstract state. So similarly, there will be a transition to self transitions to these two abstract states because there exists a transition from one the concrete state that inside that partitioning of the state. Okay. Now, of course, this one is a minimal existential abstraction because it adds only the minimal number, no more, minimal number of states that are constrained, are to be added as per the existential abstraction constraint. Okay, and similarly, so the number of transitions added is also exactly what is required and no more. Of course, you can have, so in that sense, this is minimal. You can always add more than that, and I will show you some example of that as well. For example, here in this is also bigger a little bit. Okay. I want to do this. This won't work. Okay. I have a problem with this. So let me reduce it because So this is a non-minimal existential abstraction. You see that I have why? Because, can anybody guess?
There is an extra transition from P1, not P2 to not P1, not P2.
That is right. There was an extra transition, but I've also, so this transition is not required. And I've also added willy-nilly this abstract state also to be an initial state. Okay. I could do that. I can add more things as initial initial state. So there is an initial over approximation, and there's a transition over approximation as well. And that's why you will see there are even more paths, okay, even with the same, I mean, just because due to this transition, there are already more paths than the minimal set that is quite bad, because I've added more initial states, there are also more paths, okay? So let me get back to this, okay? So now, let's try some property, okay? Let's suppose that you want to prove, now I'm getting back into the minimal version of it. I guess here I've also, no, I haven't shown it. Okay, fine. Okay, so how does it work? Once you construct this abstract model based on the predicates, now you could prove certain properties. Suppose you want to prove a property that X is, check if this is an invariant property, X greater than Y less than Y not equal to 0, which in terms of the predicates is P1 or not P2, okay? Kind of lucked out here because the property had a version, directly in terms of your predicate, but nonetheless, okay. So what you do is then you could, once you construct, an abstract version of this formula in terms of the predicates, you could check this property now on the abstract model, okay? And that's what is done, for which you can use, traditional model checking, like you can compute the fixed point, over this transition, and then you can, get the strongest invariant and then check if that, checks out. We've already seen such example, and since it is now a finite model, it is, in this case, the original model, it was potentially infinite. It is, it's an even for non-finite states, as long as it reduces the size, it may work. Now, let's see how this thing works. So this is true for the initial state, right? Because this is P1 or not P2. And as you will see, once if you use the fixed point computation to generate the set of all reachable states, and then you check along the way if the property is preserved, then this is reachable, P1 not P2. In one step, both these states, P1 not P2 and not P1 not P2 are reachable, and in both those states, this property is preserved, because what you're doing is a very weak property. It's P1 or not P2. So this over approximation that was introduced this minimal existential abstraction, although it was introducing, it was an over approximation because it had one path which was not, the path here at the bottom, which was not strictly a path in the original system. Okay, so but it didn't matter, for this particular property. Okay, so that is the idea. The idea of this predicate abstraction is if your property, is such that, if your property is such that you're only, tracking, the relevant predicates that you're tracking are those things, then you will, then you might be, that over approximation may not matter. So let's look at another property. Okay, so that's what you do. So there is an obvious question here. What happens if your property you were not able to precisely capture in terms of this? Let's suppose that your property was, if your invariant property that you wish to prove is checking if it's even of X, if even of X is an invariant, what would you do? Obviously, even of X is not expressible in terms of P1 and P2, or some Boolean combinations of P1 and P2, correct? what would you do?
Maybe enumerate the values of x, like in the whole system.
Which values, concrete or abstract? Because your goal is to prove a concrete, okay, on the concrete thing.
We have to take the concrete values, because like even in abstract set.
Yeah, but
there is
then how do you do? Then it defeats the purpose of using the abstract model, right? So, I mean, the idea is, so what you could do is you could still maybe compute the strongest, the strongest possible, the least fixed point of this model, okay? And then, when, by running the clean fixed point, you can do it. And then you take the concretized version of that least fixed point. After all, least fixed point is a formula, okay? And you are computing it symbolically, just like when you're doing abstract interpretation. Abstract interpretation, after all, computes. It generates these inductive invariants for a given abstract domain, right? So you could do the same thing here as well. And then concretize it by applying, say, alpha inverse, okay? And you can check. Then you can check if your actual property, even of x, is indeed, that the inductive invariant, because when you compute the fixed point as an inductive invariant, if that implies your property, then you're verified. If not, then of course you don't know. You have an unknown answer. So what you can do is you can still use it, just like how abstract interpreter is used to check after generating the however strong invariance that you get. Similarly, you can run that and then check if you're able to prove it. Sometimes you're able to prove it. Of course, just because it fails, it doesn't mean that that your property is false. But but at least maybe you will luck out, and then you can do it. So that is a way that you can actually do. But in the case where your property itself is thing, but usually the way this predicate abstraction is used is that all the atomic predicates that in terms of which your property is defined are usually included. Okay, so the kind of predicates that you want to use, the set of predicates, usually contains all the atomic predicates, because otherwise you may not be able to precisely prove your property for the reason that I just now explained. Okay, so in practice, you normally include all the atomic predicate corresponding to every atomic formula in your property. So that's how the initial set of predicates is determined. Okay. Okay. So let's look at another property. Here it is P1. Okay. So it is true in the initial abstract state. Okay. Because this is P1 and P2. So in one step, let's see, it is true in the state above, but obviously it gets violated in the blue state below, right? Because that is reachable. The blue state below, in which P1 is false, is also reachable. Okay, and therefore it gets violated here. So this is a spurious counter. I mean, this one is really it gets violated in the abstract state, but it is really is not a real violation in the concrete system. That's why there's nothing surprising, because this is the price that you're paying for using abstraction. So what do you do in this case? Okay, is the question. Okay, this can happen even in abstract interpretation. This can happen in any method, where you run fixed point algorithms on abstract domain as it does in abstract interpretation. So there, the idea is either in abstract interpretation, you have to use more precise domains, which for predicate abstraction means either you will have to use different set of predicates or more refined predicates. We will talk about that a little bit later. Okay, yeah, that's what I've said. So, but this is the counterexample is spurious. Okay, so there are two questions already. I mean, I have glossed over as to how you construct this abstract transition relation. And now we're also, to that, I will also add the question of how do you check if a particular example is spurious or not. So let me, okay, so that, any questions so far? I hope you understood why, why this is spurious. Yes?
Yes, sir.
Okay, good. Good, Siddharth. Yeah. Okay. Now, let's see. So before I do that, I will illustrate how this thing. Yeah. So here I showed the abstraction for for a something which was already modeled as a transition system. So how does it? How can you construct the what does it mean when you do it for constructing for programs? Okay, and as you can see, you can do it in such a way that you preserve the control structure. So I'll take a program, a software program, and see what it means to construct. Okay, what it means to do Boolean predicate abstraction on this. So here. Okay. So I will use two things, two predicates, P1, which checks if I is equal to 0, and P2, which is defined as checks if I is even or not. See, as I already told you, how do you determine what predicates you have to use? I've already said. Usually you want to include all, if not all, at least as many predicates corresponding to every atomic formula in the property you want to verify. Another thing that you want to do is you would want to include all the atomic formulas that make up the Boolean expressions in various branching constructs and loop constructs, because they kind of determine how values are propagated. Okay, that's another heuristic that you can actually use to determine the initial set of predicates. So, assuming that these are the two predicates we will use to construct the existential abstractions. Okay, so here is what. So it's in a way this what you're doing this thing is you're kind of throwing away the you're abstracting all the data type. I mean all the variables, the data type of variables. You're using kind of data abstraction in doing that, and what you're constructing is kind of Boolean programs. Okay. Because you're tracking the set of predicates. So if you, you will in your abstract program, you have a variable corresponding to every predicate that you wish to track and represent the abstract state in. And then each assignment can then be converted into. I mean, each statement here in this program will have to track what changes that induces on the Boolean on these predicates that you're tracking. This is somewhat similar to what you did in your constructing the abstract transformer for a programming language when you were doing abstract interpretation. How did you do it? Okay, so in order to construct the pose, you had to construct an abstract transformer for each of the statements in your program, and that's what is being done. is being done here. And that itself can be accomplished once you, construct a transition relation representing that captures the effect of executing this assignment statement I is equal to 0. So in this case, although I've not exactly showed you how to do it, at least what will happen if I is equal to 0, then P1 becomes true because that is tracking if I is equal to 0, so that is true, and P2 is also true because I happens to be even. Now this is even of I, therefore it is just translated into P2, and then this I plus plus, the transition relation corresponding to this is captured by these two Boolean assignments. Okay, so we check if P1 is true, then because obviously after incrementing it, P1 becomes false. But if you don't know whether it is equal to 0 or not, you can't say anything about it, and therefore star here means it can be either 1 or 1 or 0. You don't know. Okay, that is its stop. Okay, in your thing. Similarly, P2 after this assignment becomes not of P2, because as you know, if you increment by 1, it is no longer even. So this is how you do. Okay, and this itself will have to be done in a way by constructing the piecemeal transition relation for each of these things, that the abstract version of the transition relation. Okay, but the point that I want to make is, I will show you how you could do that using by turning them into using SAT solvers. Okay, but here what I want to do is, the point that I want to capture is that that you can preserve by choosing enough predicates corresponding to all the Boolean expressions here. How this can be converted into what I call as a Boolean program, which tracks the predicates. And the important thing to observe there is that while it abstracts the data into Boolean evaluations for these predicates, it preserves. You can do it in such a way that it preserves the control structure. Okay. Any questions here?
Will it always be possible to do this? Like, what if instead of I plus plus, it was some complicated expression?
Yeah, you can always make it over approximate, right? You can throw your hands up. Okay. Remember that how you did constructed abstract transformers for each things. Okay. Like I've said, I don't know. I cannot, if P1 is already false, it could be either 0 or not 0. So I can't say anything about it. Okay.
So won't it be false? If P1 is false, in that case, it will be false only, right?
No, that is right. Okay, you're right. In this case,
no, I is not unsigned.
No. If P1 is false, you know that I is not equal to 0, correct? But it is int. Huh?
So yeah, it will be incremented. Yeah.
See, in this case, for this initial state, it is true. Okay, but the idea is you want to derive this transition piecemeal individually for each of them. So if you only have to define this transition relation for this assignment statement, assuming P1, if P1 is false, unless you know that P1 will always be, so you don't know. So if P1 is false here, I is not equal to 0, so it can be negative also, no?
No, you have already initialized.
That's what I'm saying. See, if for that initial value, see, it's actually inductive invariant that this is always true. But when you construct this particular transition relation for this thing, how do you know that? I mean, I want to do it in a independent fashion, without for all, not knowing the behavior of the entire program. Okay. See, it so happens for this particular program, if it can never be negative, correct? But that means that you already, whenever I am here, I already know that I is non-negative. But that is true only for this initial state. See, so you know this only after analyzing this. Now you have to construct this transition relation in an prior to this analysis, for the entire program, without actually making any assumption about what happens to be true in all behaviors of that program. And that's why that is the challenge, okay, in doing it, okay. So that's why you will have to construct that abstract transformer without that information about the fact that how the program behaves for all iterations for this particular initial state. And that's why you can't do that without actually analyzing. It's like a chicken and egg problem, because you're trying to construct this abstract model in order to derive invariance, but you don't know without doing the analysis. Now, so if you had somehow done and you know that information, then you can actually use it. Yeah. Yes. Okay. So that is the point. I'm not sure if you're convinced. Okay. So because I want to construct the this transition.
No, I could understand. You are telling that there can be many branches and many loops, and what is the value that is coming in, that is unknown, right?
Yeah. I mean, see, in this case, because see, this statement could be, I want to construct a transition relations here such that it could be executed, repeatedly for whatever iteration. So how would I know that, for all iterations, when the control is here, that it's not negative? Okay. How do I know that?
No, if we construct data flow, right, what are the values coming in?
Yeah, that's right. So no. If you did some analysis, did some other analysis, even then this is not, then you could, okay. So here I'm not, so in that sense, that's why I'm saying you have to do some analysis, like if you did maybe abstract interpretation with interval domains, then you will get it, okay. But we are trying to construct this transition relation to do that analysis, before you do that analysis. If you had some other way, some other independent tool at your disposal to construct, those kinds of inductive invariance through analysis, static analysis, derivative analysis, then of course you could do that, okay? But without the help of that, so without thing, then you will have to do with what you what you have, okay? Yeah. So, and now I will get into how, I mean, even with this, how will you construct this kind of automate this, deriving these kind of formulas, okay, that you see on the right side for this thing, yeah. Okay, let me look at that. So the idea is the transition relation T. I don't know. He uses. You see, it's like similar to image. So the transition relation, the abstract, it should be T cap. Okay, T cap must characterize. I mean, the idea is how can we derive the formula that defines the abstract transition relations? That's the question that I'm addressing here. Okay, so that must characterize the following set. Okay. Yeah. So as long as it should characterize, it should be true for every pair S cap and S cap prime in the pair of abstract states. If there exists some concrete pair of states that get mapped to S cap and S cap prime, that is what this thing is saying. If there exists an SS prime, concrete pair of states, S and S prime, such that S gets mapped to S cap and S prime gets mapped to S cap prime, and there is a transition relation between TSS prime. This is exactly the constraint that is imposed by, you have to construct your abstract transition relation such that this condition is satisfied. And that's what I'm trying to do here. So I'm assuming that I have an arbitrary, abstract state here. I will try, I want to construct the piece wheel transition relation corresponding to this thing. Then the transition relation for the entire program is just kind of a, conjunction of those things. As we did in SSA, you could either express that in SSA notation. There is lots of different things, and that's how you have to do. And yeah. So, and how do you derive this? We want this as a formula. Okay, that is the catch. Okay. Now, why was this problem not there? How did we address this problem for abstract in abstract interpreter? So we faced the similar problem for constructing the abstract transformer. How was that addressed there? If either of you could, how did we get around this problem? Siddhant? Oh, Chandradeep. Siddhant is not. I always get.
Could you repeat once?
No. So I'm saying, okay, maybe I'll finish this and I will ask you this again. Let's I'll finish this so that I won't, so let's defer that question. So how would you, because we want a formula for this, right? Because only when we construct the formula, then we could do fixed point computation symbolically, like, we did, and you already did in one of your earlier assignments. We also saw how, if you wanted to do, programs that where the states are represented by bit vectors or so. Okay, so one way is to actually, it has an existential quantification. Okay, so you want to eliminate. One way is to, having existential quantification when you compute these to do fixed point propagation. You want to eliminate this existential quantification. Okay, so that you can have a formula. This itself is a formula. If you assume that I will include existential quantification, then of course you will have a formula. The reason you want to eliminate existential quantification is once you construct this transition relation, if you want to propagate that using symbolically, like we did like doing image computation, etc. Remember that we did that. Then you would want, if you want to use SAT solvers, the whole idea of predicate abstraction here is to use SAT solvers, okay, in order to do the fixed point computation, as we will see, okay. Then you want to eliminate. Of course, one way to do is to, you can eliminate this if indeed even your concrete system is, either you have to have powerful quantified elimination, procedures. If not, if your system is, and that is always undesirable if you have, if the concrete domain is over numbers and so on. But if your concrete domain is also finite, where it can be encoded as a bit vectors, then in principle you could, you could do it, okay? But that is not even, eliminating existential quantification. A naive way is to plug in all possible values that these pairs S and S prime can take. So that is, too many, even if it is 32-bit vector. So you want to have, you want to exploit the fact that we only have a finite set of predicates in here, over which I want to compute the transition relation. Okay, one way to do this is how most tools that use predicate abstraction do it. Now, I think, yeah, that I'm going to show here. Now I'll answer the question that I deferred. Okay, you see, when you're doing abstract interpretation, you were constructing this in the translation, because there you were not dealing with arbitrary predicates, okay, on which your abstract domain depended. There you had like interval domain, okay. Therefore, you did it by directly using the meet, join, etc. Because they were all shaped. You were able to get construct the post image as the post operator, the abstract transformer, as some simple operations involving the parameters of your abstract domain, okay, using max, min, join, meet, okay, those kinds of things, okay. That is the answer, Chandradeep, okay, that I was expecting, okay. So that's what you did. So that was possible there because you, you had, for interval domains and even other domains, that is possible because they were all nice, had certain algebraic structure, okay. And therefore, you were able to do it, in a, using those operations, which all had efficient way of implementing, efficient algorithms to compute those joins, meets, etc. Whereas here, our predicates, although we have finite set of predicates, the abstract domain, interval domain was inferred there, but still it always fit into a certain shape. And that's why you were able to do it there. You were able to exploit that fact. Now here, there are arbitrary predicates, okay? Therefore, you don't have the luxury of, exploiting its shape like an interval domain and so on. Even for the sign domain, you could, you could kind of do it, okay? Because if you already knew, for certain things, you can do it simply. But for arbitrary predicates, you will, in general, have to find a way of expressing this, constraint as a formula in terms of the predicates is what I'm looking at. Okay, but there is a way to do it which exploits the fact that we only have finite number of predicates. And that's what I'm going to illustrate here. Okay, the predicates could be arbitrary over a potentially infinite domain. Okay, but there are only finitely many predicates here. Okay, so for example, if my predicates are tracks I is equal to 1, I is equal to 2, and even up. Okay, and suppose I have a basic block in a program as I++. then, so I plus plus is the statement. So the concrete transition relation, satisfies this, is defined as here. So I prime, the successive state is I plus 1. Now we want to get a formula for the abstract transition relation corresponding to this relation representing this statement. Okay, so effectively, I want to have a formula that defines T cap in terms of P1, P2, P3, which is the tree state, and P1 prime, P2 prime, and P3 prime. Okay, so a Boolean propositional formula. That's what I want. See, there is a way to do it. Okay, since there are. Okay, is there a slide that I'm missing? Okay. Okay, this is a slide that was missing. Okay, so the basic idea here is, since we have a finite number of predicates, if there are n predicates, then there are 2 to the n to 2 to the n possible abstract transitions. Okay, because there are 2 to the n possible valuations for the various predicates, n predicates. And then that's like the bit vector, n bit vector. And then there are transitions to 2 to the n possible valuations, different valuations of the post state. Now, what you can do is, since it's finite, you can, in principle, enumerate the whole thing, which I think, and maybe that's what maybe Chandradeep, you were kind of alluding to. Earlier, I'm not sure. Okay, so you could do this. Okay, but of course, but there is a catch. I mean, although you can enumerate these abstract values, but you will have to still define these things, this formula, only when there is a transition in this concrete domain. So you'll have to take that constraint into things. So you cannot get over having to consider the concrete transition. But you can do it. See, the idea here is to use a SMT solver or a SAT solver to do it, okay? Rather than, since there are arbitrary predicates, so that's why, there is a neat way to leverage an SMT solver like Z3 to do it. What I do is, I will, for each of these possible transitions, I will check if this transition is possible. Okay, if it is possible in the concrete version. So what do I need to do to check that? Okay, so if I'm, so I will concretize these things. So P1, P2 here, it's not P1, not P2, not P3. If I is not equal to 1, I is not equal to 2, and not P3 corresponds to not even of I, and if I prime is equal to I plus 1, and I will query the solver to see if I can, I prime, if I can get to a state in which P1 prime, P2 prime, P3 prime, all of them are 0. That is, they are false. Okay, so this is the query you have to ship it to a solver. Okay, if it says it is satisfiable, then you know that there is a transition is possible. If it is unsat, then it is not possible. Okay, that's how that you will do. So if it's unsat, there you don't have to have a transition. If it's satisfiable, then you can include transitions. This, of course, it will involve an exponential number of queries to your SAT solver. Okay, in this case, it's an SMT solver because your concrete domain is integers. Okay, so whether this, for some fragment, even for if you're doing with finite state systems, then of course you will. They're all bit vectors. You can have finite encoding, and you can use bit vector solvers to do it. if there are, linear constraints, then you can do it. I mean, even this thing you may not be able to do all the time because SMT solvers are, work only for a certain fragment of, arithmetic theories. But I mean, you can do it. Certainly, you can do it for finite state systems. But there is this question, okay? Then similarly you do this, okay? If indeed this is satisfiable, then you will have one clause in here in your formula to capture T cap, okay? Corresponding to this, this transition, yeah? And now, if this is going to be, too much, okay, in the sense computing this precisely, minimally, will require you to, check 2 to the n times 2 to the n queries, okay? If that is too many, depending upon the number of predicates, you can always over approximate, okay? You can do as many, include as many transitions precisely, okay? And all the rest you can over approximate, okay? As long as you throw in those extra transitions, okay? Because you will be over approximating it. And so therefore you could get a lot of false, spurious checks, false alarms, but we will get to it, how you could fix those false alarms in an incremental way by refining on a need basis, refining these predicates and transitions, abstract transitions on a, and that's what you do, okay? So that is one of the methods that is used. And all successful tools have very somewhat sophisticated methods to do this, but basically they use SAT and SMT solvers to construct this formula in this fashion. Nowadays, you can also have limited, there are efficient limited solvers that that can solve formulas with limited number of quantifier alternations, and you can actually use them as well. Okay, so that is what is used. So, but they all use certain heuristics to. They don't compute it on all predicates, but they use certain heuristics to over approximate the transitions, and they use different methods. Some use somewhat do it on a need basis and various techniques. We won't have time to get into all those techniques, but at the basic idea, this is what they do. Okay. Now, after that, once you construct the model, then what you have is that will be my last slide. And after that, I'm done. So let me go into full screen mode. This. Skip these things. Okay, this is another example that I will get to later on. Okay, so this is what you do. Okay, this is a predicate abstraction, a general procedure for predicate abstraction that also includes a way of refining your predicates. Okay. And that's what is called CGAR, a counterexample guided, abstraction refinement as well. The first few steps here. So first, you have to determine a suitable set of predicates. Okay, I've already indicated some things. The idea is to include all predicates corresponding to each formula. I mean, each atomic formula in your thing, and also in the branching expressions in your program. You construct an abstract model, and we saw how to do that. You can either do this eagerly or lazily, and by constructing a crude over approximation to begin with, Then you model check the abstract model by computing fixed point. Now so hopefully that is scalable because you have a finite state, that's a finite state system. Then if you succeed in verifying the property, because as you know, it's a conservative abstraction, if your verification is successful, then the property is also successful in the concrete system, so you can exit with success result. But if it is false, then it could be a spurious false alarm. Then you generate a counterexample trace on your abstract model, and then you have to check if it is spurious or not, for which you will have to simulate it on the concrete model. Okay, and if it is not spurious, then you know. If it's a real counterexample, then you know it's a real error. Then also you say failure, safety failure, and then you exit. If not, you will have to do refine the abstraction, which will involve either refining your, if you're over approximated your transitions and initial state, you have to do that, or you may even have to add predicates, more predicates, or change your predicates. So in the next class, we will see some of the ideas, okay, behind doing steps 5 and 6, and that will end my discussion on predicate abstraction and C-bar. Okay, so yeah, so I'm getting close to 3:15. Maybe it's already late. So I mean, but if you have questions, I will take it, or you can. Any questions? Okay. Yeah, thanks for your attention, and I'll see you.
Thank you.
Yeah, was that a question, or you said thanks?
No, thank you.
Okay. Thank you for showing up. Okay. So I will stop sharing.